NP-complete problems. With a slight abuse of language in this subsection, we identify the language L with the problem of deciding whether X in L. Let us assume that we have a computer program that computes the prime factorization of any positive integer less than 1 billion. Let us further assume that for some purpose we need to compute not the prime factorization of n, but the number of its positive divisors. If this is the case, we cannot simply ask the program to do all the work for us, but we will see that the program will in fact do almost all the work. Indeed, note that if n is equals to p1 to k1 and p2 to the k2 times p3 to the k3 and so on times pt to the kt, where the pi are different primes, then the number of positive divisors of n is precisely pi of ki plus 1, where the multiplication is starting from I equals to 1 to t. Since m divides n, if and only if m is equals to p1 to the a1 times p2 to the a2 times p3 to the a3 and so on times pt to the at, with 0 which is less than equals to ai, which is less than equals to ki for all I. Therefore, all we need to do is to run the program, take its output, and do something very simple with it, namely compute the product of certain numbers determined by the output. The above example is a special case of a very general phenomenon in the theory of computation, or in mathematics in general, namely the reduction of a problem to another one. Indeed, the above argument shows that if we can find the prime factorization of an integer, then we can also find the number of its positive divisors. In other words, the later problem can be reduced to the former. Furthermore, the reduction did not take long when compared to the original algorithm. Think about this. So it was worth it. Of course, if the reduction had taken too long, we might try to solve the new problem directly instead of reducing it to the old one. Another example of reduction, one in which is a decision problem, is reduced to another one, will be presented shortly in the proof of Theorem 18.22. If decision problem A can be reduced to decision problem B in a short time, then it is natural to think that B is at least as hard as A in some sense. If every problem of a complexity class C can be reduced to a problem B which is in C, then it is natural to think that B has some kind of a special role in C. The following definition is the most important example for this. Definition 18.15. We say that the problem L is NP-complete if 1. L is in NP, and 2. Each L prime in NP can be reduced to L by a deterministic Turing machine in polynomial time. You may be thinking now that the above requirement is rather strong, and therefore it is usually rather hard to prove that the problem is NP-complete. Then you might be thinking that therefore the number of NP-complete problems must be small, and so their class might be a rather restricted one. The first of these concerns is partly true, namely it was difficult to find the first NP-complete problem. However, once an NP-complete problem is found, others are much easier to find because of the following simple fact. Proposition 18.16. If L is an NP-complete language, and L prime is a language so that L is reducible to L prime, then L prime is NP-complete. Proof. If A is in NP, then A is reducible to L in polynomial time, and then L is reducible to L prime in polynomial time. Therefore, A is reducible to L prime in polynomial time. Just run the two reducing Turing machines consecutively. So once one NP-complete problem is found, others can be found by showing that the first one is reducible to them in polynomial time. The more NP-complete problems we have, the easier it is to find new ones, since there are more problems to play the role of L in proposition 18.16. The notion of NP-completeness provides a strategy for those who want to prove that P is equals to NP. This is the content of the following corollary. Corollary 18.17. If there exists an NP complete language L so that L is in P, then P is equals to NP. Proof. If the NP complete language L is in P, then any language L prime in NP is also in P. Indeed, first reduce L prime to L in polynomial time by a deterministic Turing machine, and then decide L in polynomial time by another deterministic Turing machine. As we said, it was not easy to find the first NP complete language. We will now describe this language without proving that it is NP complete. Let x1, x2, x3, and so on to xn be Boolean variables, which means that they can take two values, true and false. These variables will be called literals. We introduce the operations meet, join, and bar on the set of literals as follows. 1. xi join xj is true if at least one of xi and xj is true. Otherwise, xi join xj is false. This can be thought of as the OR operation. 2. xi meet xj is true if both xi and xj are true. Otherwise, xi meet xj is false. This can be thought of as the AND operation. 3. xi bar is true if xi is false, and xi bar is false if xi is true. This can be thought of as the negation operation. A Boolean expression is just a sequence of operations on literals, such as x1 meet x2, then join x3 bar, or x1 meet x2, then join x1 bar. A Boolean expression is called satisfiable if we can assign the values true and false to its literals so that the expression evaluates to true. Example 18.18, the Boolean expression x1 meet x2 join x3 bar is satisfiable. Indeed, setting x1 equals to true, x2 equals to true, and x3 equals to false, the expression evaluates to true. Example 18.19, the Boolean expression x1 meet x2 bar, then meet the results of x1 bar join x2 is not satisfiable. Indeed, the first parenthesis will only evaluate to true if x1 is equals to true and x2 is equals to false. Well, in that case, the second parenthesis will evaluate to false. A Boolean expression in conjunctive normal form is a Boolean expression in which there are only meet operating among the parentheses. The latter are called the clauses, and there are only join operations within the parentheses. Example 18.20, the Boolean expression x1 x1 join x2, then meet x1 join x3 bar join x4 bar, then meet x2, then meet x1 join x4 bar is in conjunctive normal form. It can be proved that each Boolean expression is equivalent to one in conjunctive normal form, so restricting our attention to Boolean expressions in this form will not result in loss of generality, but it will simplify the handling of the expressions. We are now in a position to announce Cook's theorem the first result showing that a certain language is NP-complete. Theorem 18.21, Cook's theorem. Let SAT be the language of satisfiable Boolean expressions in conjunctive normal form. Then SAT is NP-complete. It is easy to see that SAT is in NP. Indeed, the witness W of x for a given Boolean expression x is just an assignment of values to the literals of x. It then takes big O of n time to verify that each clause indeed contains at least one literal with value 1. It is also easy to see that the total number of possible assignments is 2 to the m if we have m literals, so checking all possible assignments would take more than a polynomial amount of time. The proof of Cook's theorem can be found in any textbook on complexity theory. For a reader-friendly presentation, we recommended the reference 44. We pointed out that even if we only consider Boolean expressions in conjunctive normal form so that each clause contains only 3 literals, the corresponding language 3 set is still NP-complete. This is because SAT is reducible to 3 set in polynomial time, as we will see in the proof of the next theorem. Theorem 18.22. Let 3 set be the language of Boolean expressions in conjunctive normal form so that each clause contains exactly 3 literals. Then 3 set is NP-complete. Proof: it goes without saying that 3 set is in NP since an assignment of variables can play the role of the witness. We will now show how to reduce set to 3 set in polynomial time. That is, for each Boolean expression x in conjunctive normal form, we will construct a Boolean expression f of x in which each clause contains exactly 3 literals so that x is satisfiable if and only if f of x is satisfiable. We will construct the f of x clause by clause. Say one of the clauses of x is x1 join x2 join x3 and so on join xm. We will break this clause up into n-1 smaller clauses, which will also contain some new variables. In fact, let us replace xc equals to x1 join x2 join x3 and so on join xm by the clause f of xc is equals to x1 join x2 join y1 meet x3 join y1 bar join y2 meet x3 join y2 bar join y3 meet other clauses, and finally meet the clause xm-1 join xm join ym-3 bar. That is, the first and the last clause are different from the rest. Other than that, the ith clause is of the following form: xi plus 1 join yi minus 1 bar join yi. Let us replace each clause xd of x by the clause f of xd defined this way. Let us now assume that x is satisfiable. That happens exactly when each clause of x is satisfiable. As xc is satisfiable by a certain true-false assignment, there is at least one index I in m braces so that xi is equals to true in that assignment. Choose the smallest such I. Now assign yj equals to true if j is less than i-1 and yj equals to false if j is greater than equals to i-1. This assignment will satisfy f of xc since the first i-2 clauses will evaluate to true since the onboard yj variable in them will be true. The i-1th clause will evaluate to true since it will contain xi, and the remaining clauses will evaluate to true since the variable yj bar in them will be true. This assignment works for each clause of x, so we have proved that f of x is satisfiable if x is satisfiable. We still have to prove the converse. Let us assume that f of x is equals to the join of f of xc is satisfiable, but x is not satisfiable. That means there is an assignment of values to all variables xi and yj that satisfies each clause of f of x, but not each clause of x. Let C be such that this assignment does not satisfy xc, but satisfy f of xc. As xc equals to x1, join x2, join x3, and so on, join xm. This means that in the assignment satisfying f of x, the equality xi equals to false holds for all I in m braces. Then, crucially, we can remove all the xi from f of xc, and the obtained clause f of xc will still evaluate to true since no xi is barred in f of xc. This implies that yi meet y1 bar join y2, then meet y2 bar join y3, then meet so on, then meet ym minus 4 bar join ym minus 3, then meet ym minus 3 bar is satisfied by the assignment satisfying f of x. However, the last displaced expression is unsatisfiable. Indeed, to satisfy its first clause, we would have to set y1 equals to true. Then to satisfy its second clause, we would have to set y2 equals true, and so on. The next to last clause would force ym minus 3 equals to true, and then the last clause would not be satisfiable. So we have seen that x is satisfiable if and only if f of x is. As the creation of f of x takes only polynomial, in fact linear time, this shows that SAT is reducible to 3 sets in polynomial time, proving our claim. The result of Theorem 18.22 is probably optional in the following sense. If we restricted our attention to Boolean expressions which consist of clauses of exactly two literals and define two sets to be the language of those that are satisfiable, then two sets is very unlikely to be NP-complete. This is because as it is proved to be in exercise 4, this is because two set is in P. So if two set is NP-complete, then P is equals to NP. Set the reader should wait until the end of this chapter before attempting to solve exercise 4, as some additional definitions will be needed. So if 2 set is NP-complete, many NP-complete problems involve graphs, and the proof of their NP-completeness often involve the reduction of 3 sets to these problems. The reader is strongly encouraged to attempt the solution of exercise 6 for an elegant example. The following are 3 examples of NP-complete problems. We point out that the reference 15 is an entire book totally devoted to this complexity class. Example 18.23. Let ham path be the language of graphs that have a Hamiltonian path. Then ham path is NP-complete. Example 18.24. Let subset sum be the set of finite multisets of real numbers that have a non-empty sub-multiset whose sum of elements is equal to 0. Then subset sum is NP-complete. See exercise 5 for a variation of this problem. Example 18.25. Let L be the set of pairs PQ, so that P is a permutation that contains Q as a pattern. Then L is NP-complete. Note that it is very important in the above example that Q is part of the input. That is, that the length of Q is not given in advance. If the length of Q were a given constant, then the corresponding language would be in P, as you will be asked to prove in supplementary exercise 12. This is an example of an important distinction which often decides whether a problem can be proved to be NP or to be NP complete. A special case of this example is the famous traveling salesman problem. See supplementary exercise 15. Corollary 18.17 implies that if someone could find an efficient contained NP algorithm for the Hamiltonian cycle problem, or the subset sum problem, or the pattern avoidance problem, then we would know that there also exists an efficient algorithm for the several hundred other non-NP complete problems.